Hello. Okay, so I'm gonna keep talking about the some important aspects of the effective resistance problem, and a key theorem, so to speak, in this effective resistance business is something known as Thevenin Theorem. Thevenin Theorem. It's always hard to pronounce a French person's name, but I will try my best. So, so what the theorem says is roughly the following. So you're given some sort of resistor network consisting of a bunch of resistors and a bunch of batteries with their own electromotive forces. In this case, epsilon 1 and epsilon 2. And on top of this resistance network, you connect some external leads at the 2 points, which are indicated in this case by A and B. And suppose you were trying to measure the sort of resistance and the sort of voltage that would be picked up by the measuring devices at the two ends here. Then the issue is whether you can summarize the features of this entire network of resistors in terms of the overall equivalent resistance and the overall equivalent voltage. And what the theorem, so-called theorem, says is that yes, it's possible that all of these complex set of numbers, E1, E2, and R1, R2, R3, they can be all summed up in terms of a single effective resistance R and a single effective voltage E. So I'm not going to go through the proof right now, but instead talk about how one can actually then measure these two quantities, equivalent resistance and equivalent voltage, if you were an experimentalist. Okay. So first of all, how would you measure the equivalent voltage? Well, the practical answer is that you can do so by connecting these two lids to a voltmeter. Okay, a voltmeter is a device that has an extremely large internal resistance by definition. So when you hook, so basically you're hooking up this existing resistor network to yet another resistor, which has an extremely large resistance value. When the resistance is extremely large, of course, there's very little current flowing through it. Effectively, zero current flows through it. Okay. And if that were the case, then this equivalent resistance will be able to exhibit no voltage drop, because voltage drop is just I, the current, multiplied by the equivalent resistance R. However, since the current is going to zero, multiplying the current by R still gives you zero. So then there is no voltage drop across this effective resistor. So that means the effective voltage or equivalent voltage, whatever this value may be, is going to be picked up by the reading on the voltmeter. So the reading on the voltmeter must exactly equal the effective voltage of the circuit to which you're hooking up the voltmeter. Okay, so I'm just basically laying out the fundamental principle behind the use of a voltmeter to measure the voltage of some electrical device. Okay, so in practice, that's how you measure the effective voltage of any device that you're trying to probe. Okay, now suppose that you have determined the effective or equivalent voltage of some circuit in this way, and therefore has solved the question of what is the equivalent voltage of the circuit. Now, then how would you go about answering the question of what is the equivalent resistance of the circuit? Well, to determine that, you instead of connecting these two nodes to a voltmeter, you instead connect them to an ammeter. Ammeter, by definition, is a device that has extremely low internal resistance. So the internal resistance is effectively going to 0. Okay, so then it's like hooking up this equivalent circuit to a resistor, which, however, has practically 0 resistance. Okay, so therefore it does not affect the overall resistance of the circuit at all. And then if you apply the Ohm's law to this closed circuit, then obviously the relation would be like this, that the current that you are measuring through the ammeter reading is given by the equivalent voltage of the circuit divided by the total resistance. And in this case, the total resistance is the sum of the equivalent resistance plus the resistance of the ammeter. However, ammeter by definition has almost 0 resistance. So this ends up being equal to that. Okay, so now, but then we have already determined what this numerator, namely the equivalent voltage, is. Okay. But then through the ammeter, you can also measure this. So if you can measure these two quantities in the equation, then you can also derive the value of the equivalent resistance by taking the ratio of the two quantities that you have measured. You have measured this with a voltmeter. You have measured this with the help of an ammeter. You just take the ratio. And that ratio is exactly the equivalent resistance value that you have been looking for. Okay, so that's roughly the logic. Okay, so that's how you would go about determining these effective, I keep saying effective, sorry, equivalent resistances and equivalent voltages of any given circuit. Okay, so that's if you're an experimentalist, but what if you're a theorist and instead of measuring something, you want to calculate something? Okay, but of course, calculating something implies that you already have at your disposal all the information regarding the individual resistances like R and 2R and E, the electromotive force, and so on. So suppose you have information regarding all of these values. Then the question is, if you want to measure the you want to calculate the effective electromotive force or effective voltage of this entire circuit as they are connected through these two ends, what is that value? Okay, that's the question. Okay, but then you can answer this question, theoretical question, by performing a thought experiment in exactly the same way that you would have performed the real experiment. So in the real experiment, this equivalent voltage was determined by measuring or by connecting or pretending to connect a voltmeter. And instead of connecting a real voltmeter, we're going to just pretend to be connecting a voltmeter like this. Okay, so voltmeter by definition carries an infinite resistance. Okay, so therefore there can be no current flowing through this particular segment of the overall circuit. So that means you cannot possibly have any current flowing through this bottom half of the loop. All the current has to flow through the top half of the loop. But then this ends up being a very, very simple equation to solve. Namely, you have these two resistances. One has resistance 2R. The other has the resistance R, and they're connected in a series. So you just have to add their individual resistances for a total of 3R as the total resistance. And that's connected to a battery having the voltage of E. And therefore, there's an overall current of I equal to E over 3R, which flows through this upper half of the loop. Okay, but now what we want is the voltage drop between these two nodes. But that's got to be the same as the voltage drop across this single resistor of resistance R. But then that voltage drop is just the current flowing through the resistance multiplied by R. And since we already know how much current is flowing, we can just compute this and then realize that the voltage drop is 1/3 of the voltage created by this battery. Okay, so the answer we have been looking for, the equivalent resistance, the equivalent voltage is 1/3 of the voltage that occupies one of the internal organs of the whole circuit. Okay, now what about the equivalent resistance? Now, to calculate the equivalent resistance, now instead of hooking up a voltmeter, we hook up a ammeter, which by definition has zero resistance to it. Okay, but one thing we know about zero resistance in a circuit is that if some other resistance is connected to that in parallel, then this other resistance is basically rendered mute. What I mean by that is that there can be no current flowing through these finite resistance segment, because it's so much better, so much more convenient to have all the current flowing through these perfectly conducting piece of wire, and therefore entirely bypass this clumsy, bumpy road having the finite resistance. Okay, so then this resistance network is equivalent to this resistance network without this intervening resistor R, because no current will flow through there anyhow. Okay, then this circuit is extremely simple to analyze. Okay, and you can immediately read off the amount of current that passes through this circuit, and we can also invoke the previous knowledge about this this epsilon being 3 times the equivalent voltage. In other words, the equivalent voltage is equal to the current that flows through multiplied by 2/3 of the resistance R. Okay, so then what that tells us is that the equivalent resistance is precisely 2/3 of R. Okay, so as I explain this, I'm realizing that probably this way of thinking about the equivalent resistance is not entirely familiar to those of you who are trained to think about this in the sort of physics tradition. But in the electrical engineer's way of thinking, this is probably the more natural way, because they are the ones who really have to hook up a voltmeter and an ammeter to some black box of a circuit and try to determine just exactly how much effective resistance and how much voltage this stuff is endowed with. So what I have explained here is a way to formalize such a procedure by electrical engineers in terms of a concrete mathematical formulas. Okay. Okay. So this book by Purcell is famous not only for the content of its lecture, but also the content of its problems. There are some amazingly good problems listed in this book, and some of the problems require a pretty high degree of original thinking. Some of them are quite brain teasers, but others are also, they carry a pretty deep meaning. So I want to try to share some fun of solving some of these brain teasers with you. And I believe this problem was something like problem 4-7 in the book, but it doesn't really matter what the problem number was. I'm just going to explain it, the idea behind the problem. So here is this triangular bunch of triangles put together. Maybe a better way to characterize it is that you have this semicircle, and you divide the semicircle into 6 equal parts. So there are 6 points, 1, 2, 3, 4, 5, 6, 7 points at equal angles, in this case 30 degrees apart. And they're all connected to each other by a resistor. And there's another node at the center of the circle, semicircle, and this is also connected to each other. Sort of like the spikes of a bicycle rim, spikes of a bicycle ring, I should say. Okay, so every line you see here is in fact a resistor, all having the same resistance R. Okay, so I hope you get the idea of the setup of the problem. And then the fun question follows. What is the resistance between the 2 points A here and B here? Okay. Well, how would you solve that? Well, after some thinking about the strategy, probably it will occur to you that the best way to proceed is by induction. That is, first of all, you pretend that there's only one wire segment connecting the 2 points A and B, in which case the resistance is obviously R. And I'm going to take R to be 1, because R is basically just a unit, and I'm taking this unit to be to have a unit value of 1 ohm. Okay, so the next step in the progression is to think about the effective resistance, rather the node-to-node resistance R, AB, from A to B, when there are 3 resistors that are connected to each other in the form of a triangle. Okay, so this piece obviously has 2 resistors in series, and therefore end up being a single resistor with a resistance 2 instead of 1, because you have just added 1 and another 1 here. And this resistance 2 is connected to a resistance 1 in parallel, and therefore you can use the addition of 2 parallel resistors to come up with the effective resistance, which is 2 over 2 plus 1, or 2/3. Okay, so that will be the node-to-node resistance of a single triangle of resistor network. Okay, now let's put another triangle. So the bare version has all these legs carrying the equal resistance. 1, resistance 1 over here, 1 over there, 1 here, 1 here, 1 here. Okay? Now, I'm going to reduce this to an equivalent network by invoking the knowledge we already obtained from the step 2 over here. Namely, if I put together these 3 legs of a triangle, then I can treat this as if it's a single resistor whose resistance is 2/3. Okay, I mean, that's basically the conclusion that we got from this exercise. Okay, so now this 2/3 resistor is connected to this 1 resistor in series, so you just have to add the 2/3 with 1 here, and that overall resistor, okay, which I drew in this simple fashion, is connected to a resistor 1 in parallel. So since you only have 2 resistors in parallel connection, it's easy to work out the overall resistance of the two parallel resistors. And that's just this number. Now, after this much preliminary exercises, it's rather trivial to just write down exactly what will happen if you have n triangles that are connected to each other in this way, like different slices of pizza all put together into a gigantic semicircle. And this is the formula. Okay? So there's a bunch of inverses in this formula, so it's not the easiest expression to read and understand. So I'm going to cast this in a form that is much more readable. And it does look very simple after all. So what this formula tells us that if you know the node-to-node resistance from node A to node B in the case of n triangles stacked on top of each other, then you can easily deduce the node-to-node resistance when there's one more triangle added to the previous structure. Okay. So the answer to the question that is posed over here will be obtained when you just keep solving for these iteration formula until n becomes 5, I think, or 6, something like that. Okay. So now, even more interesting situation is when this n goes to infinity. Okay, so when n goes to infinity, so that means I take this semicircular ring and I cut it into infinitely many different slices. And I connect every node on the rim, and I connected every node on the rim with the point at the center, and every connection is made with the resistor having the same resistance of 1 ohm. And then the question is, what is the effective resistance between these 2 points? The axial point and some point on the rim. Well, when n goes to infinity, it doesn't matter whether n is like 1 million or 1 million plus 1, because just adding one more triangle to the existing billion other triangles is not going to change the situation anyhow. Okay, so that means in that limit, you can all treat these Rn's to be the same value regardless of the index. Okay, and therefore these limiting value of the resistance should obey this simple equation. Okay, this equation becomes this equation. And I wouldn't be surprised this equation immediately strikes some familiarity to you. Well, the solution is this famous number called the golden ratio or the golden mean. Okay. So it's quite interesting that this number, which seemed to be a highly mathematical concept, can actually arise from this very, very mundane and pragmatic consideration of what happens if you have an infinite number of triangles all hooked up together by resistors having the same resistance. Okay, and then try to measure the resistance between two nearby nodes. I mean, that seems like an extremely mundane engineering question. But then it turns out that the answer is a very elegant number. Probably one of the most celebrated numbers in ancient Greek mathematics. All right. So it may be that engineering and pure math is not so far apart as we might have thought when we didn't know better. Okay, next problem. This is a very famous problem, in fact, at least for electrical engineers. Maybe not so much for physicists, although I believe there's every reason to teach this problem and its solution to all the physics majors, because the way this problem is solved is so elegant and so much like physics that it seems to be an essential learning process to go through these steps of the proof. Okay, so here's the problem. Suppose I have an infinite square lattice of resistors. So every line segment I draw here, like this line segment or that line segment, is in fact a resistor. And every line segment has exactly the same amount of resistance. And this thing just goes out to infinity. So this is an infinite square lattice. And then I pick two nearby points, A and B. Okay. And then ask, what is the node-to-node resistance between these two guys? Okay. But of course, if you only have these 2 points and a single resistor connecting them, then the resistance by definition is of course 1, because we're going to assume that every segment is a resistor with a resistance of 1 ohm. But this segment, these 2 points are connected not only by the segment joining them, but by a whole lot of other segments. So it's like having this wire connected in parallel with many other wires. And because these different wires are connected in parallel, the net resistance is going to be less than that of an individual wire. And therefore, the node-to-node resistance, which I call RAB, has to be less than 1. But exactly how much less? What is the exact RAB value? Okay, so that's the question we want to answer. And now there's a very nice way of solving this problem without really solving anything. You just have to be able to think cleverly and use lots of symmetries and invoke the superposition principle. So let me explain to you what I mean by superposition principle later on. But first, let us start with this thought experiment. So the first step in the thought experiment is to inject current of amount A through this point, current of amount I through this point A. Okay? So the current has to move out, and then eventually current has to leave this system. But this, by assumption, was an infinite network. Okay? So the only way that the currents will be able to leave the system is for them to move out to infinity in all directions. And since there's no preferred direction, the current has to move out in equal amounts in all four directions. Right, top, left, and bottom. So then, by symmetry, the injected current I has to divide itself into 4 equal parts, and 1/4 of the current flows out through this leg. The other 1/4 goes out through this leg. The third 1/4 of the current goes out through this leg, and the final 1/4 of the current will go out this way. Okay? So between A and B, there is a resistance of R, and there is a current of I over 4. So therefore, the voltage drop between A and B, and under this thought experimental situation, is just current times resistance, which is 1/4 times R, 1/4 times I, since we assume that the resistance has a unit value. Okay, so that was a simple thought experiment to analyze. Now let's do a second thought experiment. In this experiment, we inject the current from infinity. And when I say infinity, I do not mean an infinity from a particular direction. I mean an infinity from all possible directions. Okay, so the current is flowing in sort of from everywhere in a very isotropic fashion. And then there's an extraction point at point B. And therefore, the current that you have injected from infinity all gets sucked out at this point, B. But again, there's no preferred direction in this whole thought experiment. So if this point is sucking out the current in the amount of A, then 1/4 of that current will be coming from this leg, the other 1/4 coming from this leg. This leg also carries 1/4 of the total current being sucked out, and so does this leg. Okay, so in picture, this is a situation. We have 1/4 of the current I flowing into B from all 4 directions. In particular, there's a current of 1/4 of I flowing from A to B. And such a current flow will create a voltage drop of 1/4 times I times R. But again, R is equal to 1 by our convention. Okay? So now the third part in the experiment, in the thought experiment, is to combine these two processes. You combine process 1 with process 2. And this is where the idea of superposition comes in. If something like this process 1 can happen in an electrical circuit, and something like process 2 can happen in an electrical circuit, then the superposition of process 1 and process 2 can also happen in an electrical circuit. And that's the idea of superposition. Okay? So when you superpose these two situations, then all this nonsense about current flowing in and flowing out at infinity, they cancel out. The net effect is that you inject current from point A and extract them at point B. And that's exactly the situation we wanted to consider in the beginning. Okay, so this original process can be divided into these two separate processes, and each process gave us the voltage drop of 1/4. But now, since we have to combine them, we also have to combine the voltages obtained from each process. So therefore, we have to add 1/4 to another 1/4, which is 1/2. So the answer that we are looking for is just 1/2. Okay? So the bottom line is that if you have an infinite square lattice of resistor network consisting of identical resistors, and then you ask what is the resistance between the nearby points A and B, the answer is 1/2. And what that means in practical terms is that if you were to connect the battery source to point A and point B, then roughly half of the total current flows, exactly half of the current flows through this direct link connecting A and B, and then the other half of the current flows through everything else. And that seems like a pretty neat answer to know about.